Well, hello. I'd like to offer you this nice prize. It's called the Nobel Peace Prize. Well, actually, you're going to have to do something awesome to get that. If you don't know what the Nobel Peace Prize is, you should look it up. It's awarded to someone every year for doing something awesome, pretty much. And I'm not sure why I picked this as my picture. But either way, we're going to do something awesome with math today and geometry. We're going to focus on this goal of using inequalities involving angles and sides of triangles. All right. So to do that, I want to look at this example here, this little warm-up. It says, for a neighborhood improvement project, you volunteer to help build us a new sandbox at the town playground. You have two boards that will make up two sides of the triangular sandbox. One is 5 feet long and the other is 8 feet long. Boards come in the length shown. Which boards can you use for the third side of the sandbox, and explain? So taking a look at this, if we used 8 feet and 5 feet as the two sides, could we use 2 feet as the third side? Well, yeah, we could use 2 feet. Let's start at the bottom. Could we use 5 feet? Sure, why not? 5 by 5 by 8. Yeah, I think that would work. Could we use 8 feet? Yeah, I believe 8 feet would work. We do 8 feet by 8 feet, and then it's a nice sausage triangle. Could we use 12 feet? 12 feet. Now, I think 12 feet we could use. Could we use 15 feet? So we have a 15-foot triangle side. We have a side that's 8 feet. We have a side that's 5 feet. If you look at that, 8 and 5 make 13. There's no possible way that 8 and 5 could be 15 could be the third side, because 8 and 5 cannot connect. Even if we did it this way, even if we made it flat along this, 8 and 5 just would not match up, because there's still that 2 extra in the middle that we're missing. Okay? So that's kind of a big part of what we're going to talk about today with triangles, and how the sides and angles of the triangles would have to be to make it actually a triangle. So let's start off with a couple of, we have a corollary here and a couple of theorems. Um, so looking at the essential understanding at the top, it says the angles and sides of a triangle have special relationships that involve inequality. So here's one of the first ones. It's the corollary to the triangle exterior angle theorem. So remember, the triangle exterior angle theorem says that an exterior angle of a triangle is going to be equal to the sum of the two remote interior angles, the two opposite ones on the inside. Now this corollary says the measure of an exterior angle of a triangle is greater than the measure of each of the remote interior angles. So if that's an exterior angle, then the measure of angle 1 is greater than the measure of angle 3. And also the measure of angle 1 is greater than the measure of angle 2. Because remember, those two angles add up to equal angle 1. And neither of them can be 0 degrees if it's inside of a triangle. So they have to be both be smaller than angle 1. All right, so that's a corollary. It makes sense, kind of common sense like, but it's not something we maybe thought of before. Theorem 510 says if two sides of a triangle are not congruent, meaning like xy and okay, what are we using? Xz and xy are not congruent, then the larger angle lies opposite the longer side. So basically, if we have two sides that are not the same side and it's a triangle, then we know that the large xz is longer, so the larger angle would be opposite of that side. So we would have angle y is greater than angle z. Okay, I believe that gets us into our next one. Theorem 511. If two angles of a triangle are not congruent, so it's kind of the opposite of this one. Two angles of the triangle are not congruent, then the longer side lies opposite the larger angle. So in this case, we know that angle A is greater than measure of angle B. So we know that the opposite side, so BC, length of BC, is greater than the length of AC. All right. Theorems. We're actually going to have some more. So let's just take a look at this one. I skipped number 1. But number 2 says, which are the largest and smallest angles of the triangle? Largest. Just looking at the side lengths, the largest angle has to be opposite the largest side. So since the largest side is PR, the opposite angle would be angle Q. The smallest angle has to be opposite the smallest side. So the smallest side is 3 here. That's PQ. So the opposite angle would be angle R. All right, number 3, it says, which are the longest and shortest sides of the triangle? So using that second one, since we're given the angles. Now we're given 2 angles. So we don't know yet what the third one is. But if we have 70 and 35, add those together, we get 105. And we take that away from 180. Borrow here. 5. So we got 75. This is 75-degree angle. Right there. That's actually going to be the largest angle. It's a good thing we figured that out, because then the largest side has to be opposite that largest angle. So along the side, we have to be PQ. And then the shortest side will have to be opposite the shortest angle, which is angle P. So then that leaves RQ would be the shortest side. Okay, we don't know what the lengths are right now. We just know that that's got to be the shortest side based on Theorem 511. We just talked about Theorem 511. That tells us right there. We know that would be the shortest side. Shortest among the sides. All right, here is another one that actually kind of has to do with what we talked about in the warm-up. So it says, for 3 segments to form a triangle, their lengths must be related in a certain way. Notice that only one of the sets of segments below can form a triangle. The sum of the smallest 2 lengths must be greater than the greatest length. So since these 2 add to equal 6, it can make a triangle because then the largest length is 5. Here we have these 2 add to equal 4. They would not reach to make a triangle when the largest side is 6 centimeters. So that gets us into Theorem 512. It's the triangle inequality theorem. It says the sum of the lengths of any 2 sides of a triangle is greater than the length of the third side. So you can pick any 2 sides. Any 2 sides. It could be the largest and smallest. It could be the 2 smallest. It could be 2 largest. And added together, they have to be larger than the third side. Alright, so in this case, we can do xy plus yz has to be larger than xz. Yz plus xz has to be larger than xy. And then xz plus xy has to be larger than yz. No matter what the lengths are, that has to work for it to actually be a triangle. So let's just look at a couple examples where we're given some side lengths. It says number 4, can a triangle have side lengths 22, 33, and 25? Compare the sum of the 2 side lengths with the third side. So let's try a couple different ones. 22 plus 33 has to be greater than 25. That's true because that would be 55 is greater than 25. Okay, that's good. But here's the thing, we have to do that with all of them. So let's try 22 plus 25. Is that greater than 33? Yes, because that would be 47 is greater than 33. And then the last one would be is 33 plus 25 greater than 22. Yes, because that would be 55 again is greater than 58, sorry, is greater than 22. So yes, this would be a triangle because it matches, it aligns with Theorem 512, the triangle inequality theorem. We could make a triangle from this. All right, can a triangle have sides 1, 1, and 2? Well, I'm going to find one counterexample right away that I can think of. 1 plus 1, is that greater than 2? No, because 2 is greater than 2. No. 2 is equal to 2. So essentially, if we had the sides 1, 1, and 2, we'd have a side length that's 2 here. And then we'd have 2 side lengths on top of it. And that would make a triangle. There's no inside space then. We would just make a line. All right, number 6. 2 sides of a triangle are 5 centimeters and 3 centimeters. What could the length of the third side be? So remember that third side, we'll say is x, has to be, or 5 plus 3. There we go. Those 2 sides have to be greater than the third side, or 8 has to be greater than x, or x, if you flip it around, would be less than 8. So x just has to be anything less than 8. And that's using that theorem to show exactly what we could have, anything that would work for that triangle. All right, last one. Find all possible values of x given triangle ABC, where AB is x plus 4, BC is 3x minus 1, and AC is x plus 1. So let's do this. Let's take one at a time. We know that AB plus BC has to be greater than AC. So in other words, x plus 4 plus 3x minus 1 has to be greater than x plus 1. Alright, I know that looks kind of sloppy, but if we were to combine some things and to solve this, on the left side we'd have 4x plus 3 is greater than x plus 1. I'm going to subtract x from both sides. We have 3x plus 3 is greater than 1, minus 3 from both sides. We have 3x is greater than negative 2. Divide both sides by 3. I believe I did this correctly. Hopefully I didn't make any mistakes anywhere. But then I'd have x has to be anything greater than negative 2/3. Okay, so there's one of the conditions. Now I'm going to do the same thing with a different one. Let's say that AB plus AC has to be greater than BC. So that would be x plus 4 and x plus 1 has to be greater than 3x minus 1. Alright, let's do this. We got 2x over here plus 5 is greater than 3x minus 1. I'm going to subtract 2x from both sides. And I've got 5 is greater than x minus 1. Add 1 to both sides. And I've got x 6, so, or x is less than 6. Alright? Alright, we got one more condition though. We should also say that BC plus AC has to be greater than AB. Remember, the sum of any two sides has to be larger than the third side. So here we have 3x minus 1 plus x plus 1 has to be greater than x plus 4. I have 4x over here. That'll be plus 0. It'll be greater than x plus 4. We'll subtract x from both sides. 3x is greater than 4 divided by 3 divided by 3. X plus is greater than 4/3. So there's our three conditions. We know that x has to be less than negative or less than 6. That's for sure. We have two of them where it says it's greater than negative 2/3 and it's greater than 4/3. If you look at it on a number line, let's say 0 is here. Let's say this is negative 2/3. This is 6 way over here. And this is 4/3. So we know it has to be anything greater than this, also greater than this, but less than this. So what this one right here really doesn't matter because it's included in this one. So what we could say is that x has to be anything greater than negative 2/3, and x has to be anything less than 6. Or you could write that as a compound inequality if you'd like. All right. I know that seems like a lot of work, but it's really totally just applying what we just learned with those theorems. Okay. All right. I think I'm going to leave with that. We have another one just like that you can try for number 8. And there's a theorem. I'm not going to go through the theorem right now, but I would like you to try find the error here. Think about the error here. And then the closing questions. Number 1 says, what is the relationship between the lengths of the sides and the measures of the angles in a triangle? So that goes back to the first half. And then number 2, how can you find the range of values for the third side of a triangle when you're given the lengths of the other two sides? And that's the second half of our lesson for today. All right? And they both go along with the goal of I can use inequalities involving angles and sides of triangles. All right? That was section 5-6 on these inequalities in triangles. So have a great rest of your day.